Okay, good morning everybody, and let me start by thanking organizer for having me here and also for running the StatMax show for a decade. So something I'll be talking about, which Rajesh gave a fantastic introduction, something on Mimpamba effect. And I learned this problem actually from Subir Das, when he published this paper which I edited for our journal PCCP some years back. And then I had some discussion, and yesterday Rajesh also gave a lot of interesting insight. So Vigyan is a PhD student, must be somewhere here. He really did a fantastic job, as you will see that to simulate this. And Sudeep, my colleague, who is a nucleation expert, we had some discussion with him. So this one, all of you have seen this plot yesterday, that if you have a hotter liquid, then it freezes faster, and cooler liquid freezes takes longer time. So this is the problem, and we want to see how do you understand this. First, if we can reproduce this phenomena in computer. So far it was not there actually, as I see. So this is the paper which I came to know yesterday from Rajesh. So this is one paper, 2016, where they are looking at Mimpamba-like effect in clathrate hydrates. It's a different system. And here is another paper from Burries and Linden, where they summarize most of the experimental study as of now, showing that broad trend, hotter liquid takes longer time to freeze in most cases, except this paper, the original, the Mimpamba-Osborne paper, which is the red one, which you see the Mimpamba effect. There was earlier another attempt on these from Bill Goddard in 2015. So they had, these are some of the details. So what they did, they looked at density of states. So these are the details. Looked at density of states for two different quenching from different temperature. This is the ice, hexagonal ice. And so to cut the story, I mean, they had some indication from this, from the density of states to show that probably there is some Mimpamba kind of effect. So we thought that we'll try to really first look at the whole effect, and then if we have, then we can explain. So this is really Ovigyan. He figured out over a year exactly what to do. So this is what the system details are here. So we have a hexagonal ice sheet, and we'll have a liquid at various temperature, and we'll quench it to the ice. In this case, we'll quench it to 250 actually, and we'll see whether we see Mimpamba effect. So these are, so the simulation depends very fine tuning of heating and cooling protocol. So these are all details here, so I'll skip that. So this is the movie actually, will show you actually that things works. So probably this is the first movie in the meeting, if it works. So you will see that, so this is the, at some temperature, and this is the ice sheet, and this is the liquid at some temperature, and you will see what happens over time. It will actually freeze, so quenching to 250, and you will see. So for clarity, this has been, unit cell is replicated so that you see it better. Ovisek did this movie actually. The bulk ice is hexagonal symmetry. So you can have cubic sometimes. So here we are not looking at cubic. If it is a confined water, you can have square symmetry also. So bulk ice has a hexagonal symmetry. Sometimes it can be a cubic also, but predominantly hexagonal symmetry. That's why you see hexagonal. So here you saw that the whole liquid, when you quench, actually it generates the hexagonal ice. So now what we'll do, so here I'm showing you that over time, how exactly. So typically for this case, like for this quench, it took 100 nanosecond, this liquid to freeze in this case. And then what Visek did to identify the liquid versus the ice, we calculate the Q6 order parameter. So this is the order parameter we'll use to identify the liquid and ice. And so this is the criteria we used, that for liquid predominantly here, pure ice. So this is the threshold value of Q6 will take to calculate the fraction of ice and liquid as a function of time, and will detect when is the time at different quench temperature. So here are the three different, so using that criteria, we can calculate the fraction of ice-like molecule as you saw in the movie as a function of time, how many is freezing. And so here you can see that this one is the 280. So you take a liquid at 280, quench it to 250, and that takes this much time to freeze. On the other hand, if you take a liquid at 320 and quench it to 250, this is the time it takes, and followed by this is the liquid at 360. So you see that the hotter the liquid, it takes lesser time to freeze. So these are multiple simulation averaged over. So we have different trajectories actually, just to reproduce. So here we are showing you more trajectories that you see it. Sometimes the difference between the time taken between these quenches are not significant difference. Sometimes also you have to do multiple trajectory. And also what we can say is that not any temperature you start will show this. So sometimes if you run 350, you may get out of 10 trajectories, some trajectories will show this effect. Okay. So among these, so here you see that this is what the starting temperature, and these are showing the data from three different trajectories. So this is 280, this is 320, and this is 360. So it's a Mempamba effect. So then what we are trying to debug is that what is causing this? So question we asked that what is the cause of this? Is it the structural difference between the liquid you start at higher temperature versus some dynamic effect? So to just first distinguish between that, what we can did, we take a liquid structure at 360, but then we remove the velocities at 360, we take the velocities corresponding to 250, where we are quenching. So that's what will distinguish whether it's a structural difference is causing this and versus whatever is a dynamic effect. So if he does that, then something happens that actually you don't see this Mempamba effect. So you have a liquid at 360 or 320 or 280, but the velocities, quenching velocities, you take it corresponding to 250, not the 360s. Then you do not see this Mempamba effect. You see that the Mempamba, so the cooler, the 280 freezes faster, followed by 320 and 360. So that kind of rules out that the structural difference between these probably is not causing this effect. Okay, so it must be something to do with dynamics. So that's like, it's not a done deal explanation, but then what we wanted to see that what are the dynamical quantities. So we looked at the dipole relaxation. So it turns out the dipole relaxation is very fast at 360, and that allow probably to have a readjustment to get the correct hydrogen bonding network to cool it faster, and some entropic effect. So we calculate the entropy also. So again, details we can discuss. So it turns out that the entropy of the liquid also, which is related to the very fast dipole relaxation, is also can be attributed, which is causing this Mempamba effect. So thanks for your attention. Different types of liquids like that clathrate hydrates, some experiment. I don't know, Rajesh was telling some other not so polar liquid. Is there some experiment? I don't know so far with that experiment, but in colloidal system people have shown, but not like a direct sense. There is some other mechanism which Rajesh has mentioned. Yeah, Rajesh has a comment? Question, okay. Yeah.
I also had a question. I mean, do you quench the system or do you worry about heat conduction also?
No, we just quench.
You just quench. But you have a nucleus at the side, right, from which it grows.
Yes.
You don't do spinodal decomposition or whatever, spontaneous conversion.
No, so in this way. So probably Subir will tell about that. That's what he is in the next. Yeah, we do a rapid quench.
So I had a similar question to Sanjay. I mean, so like in your setup, it seemed like you are, it's the hot liquid is in contact with the outside ice.
Yes.
So it's like.
So the hotter water is in contact with the
With
ice,
So
which
it's
is
not
maintained
like
at
you're
250.
you're not like putting the temperature inside everywhere at a lower temperature, right? You are only
The whole
except from the boundary.
liquid is connected to a heat bath.
But only at the boundary, right? Or no?
No, it's the whole liquid.
But in your like what you showed, it looked like there's water.
No,
and there's ice.
that's the way it grows. The pond grows. So, but
in the
heat bath.
No, but in the experiment, like when you put water in the freezer,
That's what it is. So it's in the ice
only at
is the freezer.
It's only at the surface that you are cooling, right? You are not cooling everywhere inside. Like
No, so that's a heat bath. The heat bath is the thermostat.
It takes the fluid at 250 degrees centigrade.
Yes, so that heat bath is
Ice at 250 degrees.
correct.
That's what it is.
Correct.
Yeah, but it's then thermal conductivity is important.
Yeah.
It's instantaneous.
Oh, why is it instantaneous? It has to go through the surface, right? I'm saying even in the experiment.
So there may be a temperature gradient or something probably immediately. So whether the temperature we can discuss. Yeah.